All righty. Good afternoon, everyone. Good to see everyone again. Or not really see everyone, but well, you know what I mean. Good to be in the same virtual space as you. So this is the first part of the week 5 lecture. We're going to be talking about light today. As a reminder, the discussion posts are due on Sunday nights, and you must also respond to 2 other people's discussions. All right, so you have to respond to 2 other people. Make sure that you do that, please, please, please. And what else? Make sure that you are getting those homeworks and labs done. I promised that I would extend the due dates, and I have not done that yet. I will do that. I apologize for not being on top of that. I will make sure that I update that in between the afternoon and evening section today. Okay. Office hours. I will be available tomorrow night from around 7 to 9, right? 7 to 9 o'clock tomorrow night. So if anybody wants to drop in for office hours, you can. And I'm trying to think anything else. I will be posting documentation on Blackboard regarding the space mission assignment that will be due. There will be checkpoints at which things will be due throughout the rest of the semester. Just to give you a little bit of a background on what the assignment is, this assignment is going to be 25% of your grade for the class. It's going to culminate in a 5-minute presentation in which you are sharing with the class a presentation that you made about a particular question that is, currently or has recently been examined through astronomy, and what sort of space mission was answering that question. What was, what did the data collection look like? All right, so you'll talk more, a little bit about like when did the space mission happen? When was the spacecraft launched? What was the big scientific question it was trying to answer? What were the hypotheses that scientists had going into the mission? What did they think that they were going to find? Why did they think they were going to find what they thought they were going to find? And then what did they actually find? And was their, was their hypothesis supported or negated by the results that they found? What does that mean for the future of astronomy? Or what does that mean about that particular question, and how astronomy might be able to further us along in our quest for more knowledge? And where is the space mission currently at? Is it a completed mission? Is it still happening? What are the expected important upcoming dates? So on and so forth. Right, so all that information will be made available in a PDF that you can download off Blackboard. And then at some point in the middle of this week, there will be space mission signups. Right, we want to make sure that not everybody has the same space mission. Otherwise, we are going to be in for a very exciting night of presentations. Very sarcastic. We want to make sure that everybody has a different space mission. This way we can all, make sure that we're getting a bunch of good information from each other that evening. And those presentations will happen the last week of classes. Okay. All right. So I'm going to share my screen. That brings us to today's lesson on light.
Professor, sorry, I have a question.
Oh.
Sure. I think who was that first? Barry, was that you?
Yes, can you hear me?
Yep.
Okay, so for the presentation, will we have to do like let's say PowerPoint or something?
Yeah. Yeah, you'll do a share screen on Zoom, and you will talk us through your PowerPoint presentation.
Okay, and one more question, sorry for that. So for the lab that was due last week, there was one question where we need to like find how long it took for the satellite to orbit around the Earth, I believe. And the animation kept stopping, and they said on the bottom, if the satellite disappears, it will come back again, or just say like retreat object or something like that. But that never happened, so I got those two questions wrong.
Okay. I would appreciate you sharing your screen at the end of class, and you can show that to me, and then I'll
Okay.
determine what
Okay.
you done.
Okay, no problem.
And then who else was chiming in just now?
It's Audrey.
Hi, Audrey.
Hi. I have a question. Are we gonna have a midterm?
Are you gonna have a midterm? No.
So the presentation gonna be our final work for the whole semester?
So if you look at the syllabus, it breaks the grading policy down into 4 areas that you're being graded on. You're being graded on your homeworks, right, and how successfully you do the homeworks. You're being graded on how successfully you complete the labs. So homework is 25% of your grade. Labs are another 25%. The discussion posts that you do on a weekly basis, all of those will be added up together, and they will make up 25% of your grades. Now we're at 75, and the final 25% is the space mission assignment.
So on the labs, I think I reached to the 5th one, but I think I have like a couple of them I didn't do too good. You think that's gonna bring me to fail, or it's okay? Because I've done my discussion boards, everything.
Let's talk more about that, because that seems like it's a little bit more personal. Let's talk about that after class. Just stick around.
Okay.
We can go through and figure that out.
Okay.
But also, folks, you know, while you can do all of the homeworks and labs now, if you wanted to, you could attempt all of them. I don't recommend doing everything now. Don't front load the course with all those things, because we haven't talked about those concepts yet, right? So if you're going by the due dates in the syllabus, right, make sure that you're always referring to the syllabus for the due dates. The due dates are set with when we're covering that material in mind. So like if I set lab 5 due for like 3 weeks from now, that's because we're not going to be finished covering what we need to know to do lab 5 until 3 weeks from now. That's kind of the idea, is that it's like paired with certain material that we're covering. Okay, in any case, here we go. We're going to start our presentation on light. So this starts with Kirchhoff's laws, right? Kirchhoff was, well, actually, you know what? 1 second. Hold on, I started with the wrong slide. This is the one that I meant to open first. I actually had the evening slide open. That was my bad. Aha, this is the one that we wanted to see. Okay. So in studying light, I want you to look at this picture. Right? And you can see how there's the one enlarged image, and then there are the 3 smaller box images on the right. And I want you to sort of look at what are some of the main differences between each of these pictures. You might notice that in the one on the top right that says Chandra X-ray, that you can't really tell. So first of all 3 of these images are of the same object. And the picture in the big picture that's blown up is the superposition of, it's all three images superposed on top of each other. So when we separate them by the kind of light that we're looking at, we can see very different parts of this galaxy. And so we're looking at a picture of a galaxy here. And when you look at the X-ray, you can see that there's a lot of activity. I'm using my mouse here. There's a lot of activity happening near the center. And then there's sort of like this cloudiness going on around it. And then each one of these dots here is another more distant galaxy. But then we switch to the optical view, right? And in this particular view, you can't, you can sort of see like there's this dark rim around the galaxy, but a lot of those stars and stuff that you see in the middle from in the X-ray picture, you don't really pick up on that in the optical picture. You can't see those things at the center of this galaxy. And with the infrared, you can sort of see that there's something very hot at the center, but there's like a kind of like a cooler region where there's not as much infrared radiation coming from it. And then there's this strong infrared region on the outer rim. And there's sort of like this glow to the galaxy. Right? And the point here is that light is not just visible light, right? Light is all of these different kinds of electromagnetic waves. All right, so let's actually start with the part of light that we know, and that's colored, right? Visible light. All right, so Isaac Newton, one of the other things that he's famous for, other than his 3 laws of motion and his law of universal gravitation, is the work that he did with optics, where he took white light, sunlight, and he passed it through a triangular prism. And if you've ever done that at home, or maybe you've seen light coming in through a glass doorway and how it sort of gets that rainbowing effect, right? The white light is dispersed into its constituent colors, right? In other words, Isaac Newton showed that white light is made up of reds, oranges, yellows, greens, blues, indigos, violets, right? All of these different colors make up white light. And then what he found, in another experiment, was that if he let only the yellow light pass through, right? If you only let the yellow light pass through after the color has been dispersed, and then you send the yellow light through another prism, what happens is the yellow light gets bent. And it doesn't turn into any other colors, right? It stays as yellow light. And this was to show that the prism didn't actually add or remove color from the white light. It just separated the different colors that made up white light. It's like putting the yellow light through a prism on its own didn't turn it back into white light. It didn't turn it into blue light. It turned it into green light. All right, so color is an intrinsic property of light. The color has nothing to do with the prism. Right? The prism did not create these rainbow colors. The rainbow colors were already part of the white light. But as I was mentioning a moment ago, visible light is but a small fraction of the electromagnetic spectrum. Right? Light is an electromagnetic wave. And what that means is it is a wave made up of electric fields and magnetic fields that are oscillating and can travel through empty space. But we have all these different kinds of electromagnetic waves. And if you look at the top here, right in the middle of this electromagnetic spectrum, visible light, all of the things that you can see with your eyes, right? Essentially, if you can see it with your eyes, it's visible light. Falls in this tiny little sliver of the spectrum, right? So there's so much other kinds of light that we can't see, right? There are things that, you know, we know of, like radio waves, microwaves, that are technically light, right? They are electromagnetic waves. They are light. They're just not the kind of light that we can see with our eyes, right? But like X-rays, gamma rays, ultraviolet rays from the sun, our eyes can't detect those, but they are there, and they are electromagnetic waves. So when we talk about these waves, there are a couple of ideas that we need to know, and that has to do with wave characteristics. So I'm going to draw here. I'm going to just pop on over to my iPad for a moment. Here we go. Okay, so this is an example of a wave. All right, and what you'll notice here is that the wave is a repeating pattern, right? It is like a sine curve. Right? In math, we call this a sine curve. And this red line that I'm drawing through the middle is sort of like that midway point, and we call this the equilibrium position. And from here, we can describe how much this wave is vibrating, right? What is the amplitude of the wave? How big is the wave? Right, so we can measure its amplitude off of this line. How big is the wave? We can also measure what's called the wavelength, which is how long the wave is. All right, so if you're counting the boxes, how long do you think this wave is?
Two boxes up, and oh no, actually, oh, long. Never mind.
How long is it?
17, if I counted correctly.
You did not count correctly.
Oh, I didn't. 16. Sorry.
16. So how many of you agree? 16. This wave is 16 units long.
I don't think it is, because it's in a wave. If you stretch it out, it would be longer.
Well, but we're not stretching it out.
Oh, then yeah, then it's 16.
All right, so how long is this wave? Well, I guess you could say that this whole thing goes 16 blocks over, but that's not the same as the wavelength. Right, so wavelength is how long one wave cycle is. So a wave cycle is one cycle of the wave before it repeats, right? So you can, how many times does this wave repeat itself? Well, it almost looks like it's the same image twice, placed side by side, where this is the wavelength. The wave starts here and ends there, and then it repeats. Right, so we got this sort of repeating sine wave pattern. And this is the wavelength, which in our mathematical formulas, we denote with the Greek letter lambda, lowercase lambda. Okay, so we've got wavelength. We've got amplitude. All right. But then there's another thing, another characteristic of waves that we can't quite capture here in this still image. And that is something called frequency, which if you use the word frequent or frequently, or maybe you even use the word frequency in your daily lives, this might make a little bit more sense to you. Our frequency is how often does the wave repeat itself, right? How frequently does the wave pattern occur? So like we can have, here, let me get a better drawing here. All right, we can have this kind of wave repeating itself, every however often, or we could have a wave like this, that repeats itself more frequently. Oh, my hand slipped. I'm just going to draw over it. Yeah. Or we could have a wave that repeats itself less frequently. Right? So what we kind of see here, and I'm going to just rearrange this very quickly. As we're going from the top wave, wave 1, down to wave 2, down to wave 3, right, we have the wavelength is getting bigger. Right? Wavelength is increasing. Right? In the first one, the wavelength is 2 boxes, but in the second one, the wavelength is 4 boxes, and in the third one, the wavelength is 8 boxes. However, the frequency of the waves is decreasing. Right? Assuming that all 3 of these move at the same speed, side to side, or from left to right, the wave, we'd encounter new waves more frequently on the first image than on the third one, because of how closely packed they are. We will get more waves more frequently. So frequency, which is F, decreases. Frequency decreases. Okay. So we have all these different kinds of waves: gamma rays, X-rays, ultraviolet rays, visible light, infrared light, microwaves, radio waves. Okay, 7 different kinds of electromagnetic waves on this spectrum. And the thing that we use to differentiate them is their wavelength and their frequency. Right? It's how often, or how frequently do these waves vibrate? Do they vibrate very slowly, or do they vibrate very quickly? Are they very long wavelengths, or are they very short wavelengths? And so in the second line on, let me go back to the PowerPoint. In the second line on the PowerPoint, you can kind of see there that we're comparing the size of a single wavelength to certain objects. So like visible light is about as long as a single bacterium. Infrared light is about as long as a pinhead or an animal cell. But a radio wave could be, or a microwave could be as wide as a baseball or as long as a football field. Right? And then if you go towards the left on this axis, the wavelength gets shorter. You know, X-rays are like the size of a hydrogen atom. Gamma rays are even smaller than that. And so you can see, going to the left, we have shorter wavelengths. Going to the right, we have longer wavelengths. And you can see it just in the spectrum itself, that the wavelengths are longer for radio than they are for gamma rays. And then we have frequency. And what you'll notice there is that the frequency scale is kind of the opposite, right? If we move in the direction of shorter wavelengths from right to left, that is the same as going towards higher frequencies, right? Shorter wavelengths of light oscillate more frequently than longer wavelengths of light. All right, and then at the bottom here, just under frequency, we have energy. And the energy of these different kinds of electromagnetic waves also varies greatly, on orders of quadrillions of many powers of 10, you know, quadrillion times differences. So gamma rays are incredibly energetic electromagnetic waves. They can do a lot of damage to your skin. That's why we try to avoid things that have gamma radiation or X-ray radiation and even ultraviolet. But then these longer radio waves or infrared or microwaves on the longer end of the electromagnetic spectrum, they carry less energy, right? So basically, waves that have greater wavelengths vibrate less frequently. If you're looking at my hand, which is sort of showing frequency as a way of sort of determining energy, not much energy. But gamma rays, which have a high frequency, a lot of energy, right? The higher the frequency of the wave, the more energy it has. Okay, so that's something that I would make a note of. And so what are the sources on Earth of these different kinds of radiation? Well, as far as gamma rays go, we have radioactive elements. Right, we have like uranium, plutonium. For X-rays, we have X-ray machines, which we use to look at inside of our bodies. For visible light, we have the light bulb. Ultraviolet, we have like tanning booths. Infrared light is given off by people. Yeah, you all give off light, just not visible light. And you can feel that infrared as heat, right? You ever like have somebody put their hand near you, and if your eyes were closed, like you would know that there's something there because you can feel the heat hitting your body? That is infrared coming off of another person. All right, and then we have microwaves and coming from microwave ovens, and radio and microwaves coming from radar and radio transmitters. All right, so we've got all of these different sources on Earth, but then we have sources that are not on Earth, that are, hold on a sec. There we go. Cool. Sources that are not on Earth that emit these kinds of radiation. So like gamma ray are found through gamma ray bursts, and X-rays you can usually find coming from black hole accretion disks, which we'll talk about. And ultraviolet and visible light come from the sun or the sun's chromosphere. And infrared light comes from planets and clouds where stars form. And radio waves and stuff come from the cosmic microwave background and radio galaxies. And so there are all of these different things that are out there in the universe that we can't actually see if we're only looking at it through visible light. Right? So one of the tools, the most important thing that astronomers use to measure the universe is light. right? We have to use light from all the places that we can't go to. But if we're limiting ourselves to visible light, then we're actually missing out on a lot of what's there, right? Just to go back to this image, right? If you're only looking at visible light, you're missing other parts of the bigger picture. And so in the electromagnetic wave, in the electromagnetic spectrum, we have radio waves, which come from pulsars, infrared light, which comes from cool objects like planets. I say cool objects, but basically I'm saying things that are not hot enough to be stars. Then we have visible light coming from nebulae in the universe. Anything that can reflect light can be seen, or rather anything that we can see with our eyes emits visible light or reflects visible light. Right, so you can see here, this is a picture of Jupiter in 1994. This is looking at Jupiter just through the infrared part of the spectrum, which allows us to see areas of heat. So you can sort of see where Jupiter is hotter and where it's colder based on this color scheme that's used. Here's Saturn being looked at in radio wavelengths, right? So we're exclusively looking at Saturn in radio waves, and you can sort of see here how you can make out Saturn's giant ring. You can see where the ring cuts in front of the body of the planet, and you can see that there are more strong radio waves given off by the planet itself than by its icy ring. Right, here's a visible spectrum rendition of a planetary nebula. And then we have ultraviolet, which comes from very hot stars and hot gas. We have X-rays, usually coming from neutron stars or black holes. And we have gamma rays, which come from these events called gamma ray bursts. And again, each of these paints very different pictures of our universe. So what exactly is light? Well, there are two different ways of thinking about it. The first is that light is an electromagnetic wave, and waves transmit energy. Just think of the ocean, right? The waves of water that you see in the ocean, they don't actually move water over very much, but they allow energy to transfer, right, through the water. The water is the medium by which the energy moves. And in space, we have these electromagnetic waves which transmit energy across vast distances. The other way of thinking about light is as more of a particle than a wave. So we're going to look at these different complementary ways of describing light when it's most, depending on how convenient it is for us to pick one over the other. Right, so depending on the properties of light that we're looking at, it might be more convenient to describe light as a wave. Other times it might be more convenient to describe it as a photon, which is a particle of light. And what makes these photons different, I suppose, is that a single photon or a single particle of light carries a very specific amount of energy. Okay, so this is what I meant. This is what I was getting at before. You can see here the wavelength, right? The wavelength is going from, in this case, it's slightly different than the drawing that I did before. Here we're looking at going from one crest to the next crest of a wave. Crest is the top part of the wave, the trough is the bottom part of the wave. Essentially, the wavelength is how long a wave is before it repeats itself. So we could have measured the wavelength by going from trough to trough. We could measure it by going from the start of the sine wave to the next time it repeats itself and we get back to that same spot. where the frequency, as I mentioned, is the number of waves passing a point in space every second. Right? So waves that have higher frequencies have more waves passing through in the same amount of time as another wave. When we measure frequency, the unit of measurement that we use is called the hertz, which is equivalent to 1 cycle per second. So let's say that I blink, right? For me to blink my eye, from open to close back to the open position takes 1 full second, right? And so if I'm blinking my eyes like that, then I'm blinking them with a frequency of 1 hertz, 1 cycle per second, right? I could clap once every second, and I'm clapping at a frequency of 1 hertz. All right, we are actually used to describing frequencies, but not usually in terms of hertz, in terms of beats per minute, right? Think about like when you take a pulse, right? What's a person's pulse, right? It's how many times their heart beats per minute. Beats per minute is the same as, is equivalent in a way to cycles per second, right? It's how often something happens in a certain amount of time. And so we have a very special relationship here between frequency and wavelength, and also the speed of light. And so the speed at which light travels is the connecting factor for these two. You could rearrange this equation so that it says the speed of light equals frequency times the wavelength. If you multiply wavelength up like this, so that cancels, right? C equals f times lambda. And an important thing worth noting is that all of those different parts of the electromagnetic spectrum, all of those different kinds of waves travel at the same speed. They all travel at the speed of light. So blue light travels just as fast as red light, travels just as fast as X-rays, travels just as fast as radio waves, travels just as fast as infrared light. So take a look here. You go ahead, please type your answer into the chat. It's a multiple choice, looking for that participation today. All right, I'll read this out loud. Red light has a frequency of 430 terahertz, tera meaning 10 to the 12th power. And blue light has a frequency of 758 terahertz. Which travels faster? A, red light, B, blue light, or C, they travel at the same speed? Everybody needs to type into the chat. Still waiting on some of you. Now I feel like y'all are just saying B because one person said it. Why are we saying B? Tiffany, why did you say B? There are smaller waves, there are more of them. Okay. Blue light has a higher frequency. Therefore, you're saying it travels faster. Jasmine, why did you pick C?
Because light is light. So I figured they travel at the same speed. One might just be a little brighter than the other, which would be blue.
Okay, so but we're not so concerned about the brightness, but I like that you're thinking about that. But remember what I said a moment ago, everyone, that all light travels at the same speed, right? I just followed up with a question that I answered for you. Right? I said blue light travels at the same speed as red light, travels at the same speed as ultraviolet, travels at the same speed as X-rays, travels at the same speed as infrared light. You know, so they all travel at the same speed. The difference between blue light and red light, even though they travel at the same speed, is that they have different frequencies. And so blue light is a higher frequency kind of light, and red light is a lower frequency kind of light. And so just in the visible spectrum, you have blues and violets at one extreme and reds at the other, and then green is sort of in the middle with a wavelength and frequency that's, you know, right between the other two. Okay, so they all travel at the same speed. We need to know that. They all travel at the same speed. Okay, so there's another bit here, and I'm not going to get too much into this right now. I'm not going to get too much into the history of it, but actually, I am going to pull up a simulation if it's still available online, because they recently removed all simulations that use Java. Hold on one second. Let's pull this up. Okay, here we go. So back to that slide for a moment. I just want to make sure that the simulation was there, and it is. So light, we said, behaves like a wave, but it also behaves like a particle. And when we treat light as a particle, we think of these particles as individual little packets of energy, which we call photons. And every single photon carries a different amount of energy. If you look at the bottom here, right, this is an incredibly important equation, right, which relates energy of light to the frequency of light. So if I were to highlight this, right, the energy is equal to this constant times frequency. Right, so light that has a higher frequency carries more energy. If you go back a slide, between blue light and red light, even though they travel at the same speed, blue light has a higher frequency, and therefore blue light carries more energy than red light does. Okay, so back in 1905, Albert Einstein conducted an experiment by which he proved something called the photoelectric effect. And this basically proves that light behaves like a particle. not only like a wave. Thus, we call it the wave particle duality of light, that light can behave both like a wave and like a particle. So let me go over to the simulation now. Okay. Give it a second. It wants to take its time. All right, so we can all see the shared screen, correct? Okay, thank you, Jasmine. Okay, so here's what we're looking at. There is, you can ignore this battery because it has no voltage. Just consider this one giant wire that goes around. And there are these two plates. And the two plates are inside of this glass tube. So no material is getting in, no material is getting out. And the plate on the left has this thin metal surface to it. You guys all see that? It looks like a little a little gray rectangle. Well, up on the top here, we have a lamp. And this lamp we can turn on and it shines light on to the surface. Now, as we take this slider here and we change the color of our bulb from these deep reds to these higher frequency colors, right? Remember, blue is high frequency, red is low frequency. If frequency goes up as we move to the left, then wavelength is going down, right? So blue light has a shorter wavelength than red light, which is why blue light has a higher frequency, because it's a smaller wave. Now, as I move the slider over, we're shortening the wavelength, but we're increasing the frequency. We just mentioned that frequency and energy are very, very closely related. So we're getting towards higher energy light. Let's watch what happens. So right now we're on 554, 552, 549, 543, 541, 538. So as soon as we got right around this particular color of light, the light started having enough energy to free these electrons, right? These blue dots are all electrons, and they are being ejected from this plate. But light that had less energy couldn't do that. Right? Light that had less energy could not eject these electrons. But light with more energy can. So why is that? Well, maybe we stop thinking about this in terms of like a constant stream of light and think about it as a beam of photons. Because this is really all that light is. It's a bunch of little photons, a bunch of little particles of light. And as these particles of light hit the atoms on this metal sheet, if they hit the right spot, they can free an electron from the surface of the metal and get it to travel across to the other plate. As we increase the energy of these photons by going towards the shorter wavelength, so if we go from green to blue, that's the higher frequency, more energetic light, watch what happens to the electrons that get kicked off the metal. They start moving with a greater speed. than the ones from earlier. We can also change the intensity of the light. The intensity of the light is related to the brightness. Right? If we release more photons, we have a higher intensity of light, we can get more electrons ejected off the plate. And if we go even higher energy, higher frequency visible light, we can get even faster moving electrons. Right? And this is to show that the photons, the particles of light, are individually hitting electrons and ejecting them. And we can go into the part of the electromagnetic spectrum that we can't actually see, and we even get faster moving electrons, because this kind of light carries even more energy. Right? So this is a very important discovery. So let me go back here to our slides. Right. So we said that what came out of this experiment was this relationship here, that the energy of light is equal to this constant times the light's frequency. So higher frequency light has more energy. We'll take a moment to answer this one. Jasmine, is this why it gets hot under a spotlight? Well, under a spotlight, you have very intense concentrated light. So yes, it's like I mean, you could say that this is why it gets hot when you step out into the sunlight. If you're standing in the shade of a tree where it's a little bit cooler, and then you walk out right into the direct sun, you're going to feel it get hotter on your skin, because it carries more energy. All right, so folks, let's pick one of these three answer choices. All right, I'm not going to go forward until everybody responds. So Barrier, I'm going to come back to you in a second for you to explain your thinking there. But let's get more responses. That's one person out of 18. Still need 17 of you to respond. Still waiting. Barrier, why did you say B?
I believe it's B because in the previous like animation that you showed us, when you projected the light with higher frequency and shorter wavelength, that's when the protons, that's when the electrons started getting detached, and those are part of energy, I'm assuming.
Mm-hmm. But also look here. Remember what we said a moment ago? It was, I think, back on this slide, where we said that frequency is equal to the speed of light divided by the wavelength. And so frequency and wavelength are inversely proportional. If wavelength gets bigger, frequency gets smaller. If wavelength gets smaller, frequency gets bigger. And so if energy is directly proportional to frequency, then energy should be inversely proportional to wavelength. In other words, a shorter wavelength would mean higher energy, and a longer wavelength would mean less energy. And so that's what we're saying here. The higher the photon energy, the shorter its wavelength, because a short wavelength means high frequency means high energy. Okay, very good. So now we're going to redirect our conversation a little bit here and talk about atoms. So we know that atoms are basically the building blocks of all matter that we interact with, and these atoms are composed of subatomic particles like protons, neutrons, and electrons. And inside of an atom, at the very center, is a nucleus, which is where all of the protons and the neutrons are located, at the very, very center. And the electrons orbit around that nucleus in like a cloud, like a fuzzy cloud. Right? And we call it a cloud because we don't really know exactly where the electrons are, other than the probability of where you are most likely to find them. Right? So like you can see how in this cloud, it's more dense towards the center. You're more likely to find an electron in that region than in this outer region where the cloud is not as dense. Right? And these atoms are held together by electric forces and also something called a strong force, which we'll talk about later on in the course. Right? But the electrons are bound to the atoms by this electrostatic force. And these are really small particles. Like an electron is 3 × 10⁻15 meters. That is tremendously small, right? I mean, you can't see anything with your eyes really much smaller than 10⁻⁴ power. I want to say somewhere around there, maybe 10⁻⁵. And this is, 10 billion times smaller than that. So we're talking about very, very small things here. Right? And there are some terms that we should know. Right? If you've ever taken chemistry, some of these words will seem familiar to you, like isotope and molecules, atomic number, atomic mass number. So every atom on the every element on the periodic table of elements is based on the number of protons in its nucleus. So if something has 1 proton in its nucleus, it is hydrogen. Right? Doesn't matter about all the other things. Doesn't matter how many electrons it's holding on to or how many neutrons it has in its nucleus. If something has only 1 proton, or it has an atomic number of 1, it is a hydrogen atom. If something has 2 protons in its nucleus, it is a helium atom, right? Atomic number 2. Anything with 6 protons is carbon, right? then there are certain atoms like helium, which naturally has 2 protons and 2 neutrons in its nucleus. Right? The atomic mass number is the sum of all of the protons and neutrons in the nucleus. So helium has an atomic mass number of 4. Hydrogen, which only has a single proton, has an atomic mass number of 1. Notice how for each of these atoms, the number of electrons is the same as the number of protons in the nucleus. So if something has 1 proton, it can hold on to 1 electron. If something has 2 protons, it can hold on to 2 electrons, so on and so forth. Okay, now back to what I was saying a moment ago, how, something that has 6 protons in its nucleus is carbon, but it can have more than 6 neutrons, right? And still be carbon, because it would still have its 6 protons. So down here at the bottom, we have carbon 12, which is the one that we saw up top on the right, where there are 6 protons and 6 neutrons in the nucleus, hence the atomic mass number of 12, carbon 12. But you can also have an atom of carbon that has 6 protons and 7 neutrons. So it's carbon 13. And over here, 6 protons and 8 neutrons, it's carbon 14. They're all carbon, but we call them different isotopes. Right? So isotopes of a given element contain the same number of protons, but different numbers of neutrons. The other term is a molecule. Right? So an atom is a single element. A molecule is a combination of 2 or more atoms. So like the air that you breathe is O2, it's dioxide. Carbon dioxide is a carbon atom with 2 oxygen atoms. H2O, water, is 2 hydrogen atoms and 1 oxygen atom. And so that's what makes it a molecule, is 2 or more atoms combined together. All right, so to summarize what we just learned. What is light? It is energy. All right, light comes in many colors, and when the visible, the different kinds of visible light come back together, they form a white light. Light is a wave, but we can also think of it as a particle. So light can be treated as individual pieces called photons, and every photon of light, every light particle, has a very specific wavelength, frequency, and energy. Right? We said that the frequency and wavelength are inversely proportional, meaning if one gets bigger, the other gets smaller. Right? So a short wavelength means a high frequency. We also said that frequency is directly related to energy. So the greater the frequency of a ray of light or of a photon, the more energy it carries. Right? And gamma rays, which have the highest frequency of all of the lights on the spectrum, carry the most amount of energy, where radio waves, which have the lowest frequency, carry the least amount of energy. And these are all the different forms of light. There are 7 here: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. That's in order of increasing energy or increasing frequency or decreasing wavelength. But what is matter? Well, matter is, or at least ordinary matter, is made of atoms. So things that are made of protons, neutrons, and electrons are considered matter. And we sort of alluded to it earlier, right? But there's a lot that we can learn from light, right? So we can answer some of these questions, like why are certain stars different colors? And how is it that we know what a star that is millions or billions of light years away And how do we know what they're made of? All right, we obviously have never been to any other stars. You know, we've never been to any other planet, at least not as a species. Right? We've been to the moon, but we've never gone to a distant planetary system. You know, we've never left our Milky Way galaxy. So how do we know what objects that are outside of our galaxy are made of? Well, light allows us to answer all of these questions. Right? It also allows us to determine the motions of stars, figure out what stars are doing just by observing the light that they're emitting or reflecting. And so when light travels, right, when light propagates, that's the word that we will most often use. When light propagates, it spreads out as it travels. Right? So think about that. If you have a light bulb, the light coming off that light bulb is spread out over a large spherical area that grows and grows and grows as the light travels away from the bulb. In the same way that you can imagine little drips of water hitting a very still pond, and how the ripples of that water just propagate outward away from the spot where the droplet hit, and how that ripple grows into a very large circle. And the farther it travels, the more spread out it becomes, the more distributed that energy is from the ripple. Right? So light is exactly the same way. Right? And we say that it obeys an inverse square law, which basically means that it is the strength or the intensity of the light is inversely proportional to the square of the distance that it travels. So like in going from position 1 to position 2, you could probably say that it doubled its distance from the light bulb. Going from 1 to 2, it doubled its distance. So if it doubled the distance, then what happens when you take that factor of 2 and you square it? It becomes a 4. Right? And so when it doubles the distance, you can see how that same amount of light gets spread out over 4 times as much area. And therefore, if you were standing in any one of these smaller squares, the light would appear 1/4 as intense. Okay, and so was born this branch of science called spectroscopy. And in this branch of science, there was a young scientist, Joseph von Fraunhofer. I can't recall off the top of my head which country he's from in Europe. I know it starts with a B, but it's escaping me. Maybe it's Bulgaria. I think he's from Bulgaria. And he looked at a beam of sunlight and he kind of did what Newton did, which was he put that light through a prism. And in doing so, he looked even more carefully than Newton did and found that there were actually little dark spots in the spectrum that was created from white sunlight. So instead of just seeing a continuous rainbow, which is oftentimes what you see when light comes in through a window and it hits a piece of glass and you get like a short little rainbowing effect, if you look really closely, and you will never see this with your own eyes, but if you like take a magnifying glass to it, maybe, you'll see that there are these dark patches here, areas where the light is less intense. And so we started to wonder, well, why are some colors, why are some very specific frequencies of light missing? So in 1857, right, a little bit more than 40 years later, we have these other two scientists, Robert Bunsen and Gustav Kirchhoff, who were playing with elements in a lab, and they were shining light through them and capturing the kind of light that was able to pass through. And what they found was something very important. They found that every single chemical that exists, every element, has its own unique spectrum. So the spectrum that comes from hydrogen is very different and unique from the spectrum that comes from helium, which is unique from the spectrum that comes from carbon. Let's elaborate on this a little bit now, and then I'll pick up with the rest of it later on. All right, so there are 3 laws, which we call Kirchhoff's laws. And this is sort of the lead up to those laws, right? So this is kind of like the experiment you can imagine that Kirchhoff had set up. And he has this hot light bulb. And a hot light bulb emits all colors of light. Right? This is like an incandescent bulb. Emits all colors of light. And what he did was he allowed a sliver of that light from this hot bulb to pass through a slit in a board. And from that slit, the light coming from the bulb hits a prism. The prism disperses that white light into all of its constituent colors. And as they leave the prism, they continue to spread out, and they are then displayed on this screen in the back. And you see a continuous spectrum. There are no breaks in the spectrum, no black lines. And then he takes the hot bulb, and between the bulb and the slit places a cool gas. And he can do this with every element. He can do a gas of hydrogen, gas of helium, gas of whatever. Right? He just has to get it hot enough to turn the element into a gas. And he passes the light through the gas, which goes through the slit, which goes to the prism, which gets dispersed by that rainbow effect. But what he noticed when passing the hot bulb's light through the cool gas is that some of the colors didn't make it through. If you can see here, there are some black lines in the spectrum, some colors that are missing. And you wonder, well, why are these colors missing? And so this cool gas then got hot, and he took the hot gas, so we can ignore the hot bulb, right? Because this light from the bulb is not going through this slit over here into the prism. The only light that's going through this slit and hitting that prism is the light coming out from this gas, the light that the gas itself is emitting. And that light goes through the slit, hits the prism, gets dispersed, and we get these a mostly empty spectrum, right? It's very dark, there's no light there, but then there are these very specific colors, very specific bands that show up. We call this the emission spectrum, because this is the spectrum being emitted by the cool gas. Over here in setup B, we're looking at what's called the absorption spectrum, showing which colors were absorbed by the cool gas that weren't allowed to pass through. And over here we have that continuous spectrum. Right? And we're going to come back and make the connection between the emission and absorption spectrum in just a second. So we have a hot light source, produces all wavelengths of light, all visible wavelengths. That light passes through a prism, which gets cast onto a screen. All of the colors show up, right? It is a smooth, continuous rainbow. Now, if you're looking at the bulb may not appear white. It might appear like a yellowish, orangish color. That doesn't mean that it's not emitting purples, blues, greens, and reds. It just means that the yellows and oranges are being emitted at a higher intensity. And so That's just, I know some of you may have been saying, well, how could your everyday incandescent light bulb, emit all the different colors of light? Even if it looks yellow or orange. And it only looks yellow and orange because those colors are coming through more intensely. And so that's what this is showing. Then let's move on. I'm actually going to come back to that. This is the absorption line spectrum. So you have the hot light source. The light is passing through this cloud of cooler gas. The atoms in the cloud absorb that light based on what the cloud of gas is made of. So depending on what kind of element this gas is, determines which colors it's going to absorb. And then the light that makes it through goes through the prism, and we get this, right? These dark absorption lines, right? These absorption lines correspond with the wavelengths that the cloud of gas absorbed. And you can see how the intensity dips at those wavelengths, at those absorption lines. It's like this yellow, that orange, this red, they don't really make it through as intensely because the cloud of gas absorbs them. And now let's look at the emission line spectrum. So here, the gas itself is warm. And this gas is emitting light, but it's not emitting light of all colors. It's only emitting very specific wavelengths of light. Again, based on what it's made of. And what we notice here is we have a mostly empty spectrum, zero intensity at these wavelengths, but we get maximum intensity at these wavelengths. Right? Notice how this cloud of gas, which appears like a bluish greenish color, has very high intensity blue and green lights and less intensity reds and yellows. Right? And so that's why it appears more blue, even though it is emitting all of the other colors. Now, as I toggle back and forth between the emission spectrum and the absorption spectrum, notice that they are inverses of each other. Right? So the light that the cloud of gas absorbs, those colors that are being absorbed are then colors that get emitted later on. Right? So there's something about these specific wavelengths of light that are important for this element, for this material. And therein lies Kirchhoff's laws, right? His three laws. Right, so a hot dense object, such as a black body, we will define black body in the evening section, radiates at all wavelengths and produces a continuous spectrum. Again, you can see there are no breaks in the spectrum here. Right? And then if you have a cool, low density gas that we're shining light through it from a continuous source, there are going to be certain colors that are missing. These are the colors that get absorbed by the gas. And then if we're just looking at the colors coming from a hot, low density gas, we call this an emission spectrum because these are the colors of light being emitted by the gas, and how these colors correspond with the absorption spectrum. Right? These are like inverted images. All right. And with that, we are done with our presentation today. So with that, if you'd like to head out, you can. I'm going to stick around for anybody that has questions. I know that there was a question earlier. I think Audrey, I think you said you had a question. Maybe I'm mistaking you for somebody else, or I think.
Yes.
I had a question too.
You're also right. Okay. Okay. So I'm going to close the slides. If you'd like to head out, you can. And I will now take some questions. So what do we got?
So I was saying,